So today we're going to look at how radioactive materials decay. And we're going to look at alpha decay, beta minus decay, beta plus decay, and gamma decay. Now it all hinges on this graph here, which shows the number of protons against the number of neutrons, which is the mass number minus the atomic number or the proton number. Now you can see that these dots here are all the stable nuclei or elements on the periodic table. And this line here shows you the line where the number of protons equals the number of neutrons. And you can see that as the nuclei gets heavier, or the element gets heavier, and the atomic number goes up, you can see that it needs more and more neutrons to enable the nucleus to be stable. And so when the nuclei is out of this region, it will decay in order to become more stable, emitting radiation which is ionizing and is random, and that's why these materials are radioactive. So let's first have a look at an alpha decay. Now alpha decay is proton rich, so you can see alpha decay happens with heavy nuclei which are in this region up here. And so what they need to do is they need to decay those nuclei to move into this area by changing into a new element. So the parent nucleus decays into a daughter nucleus, which is moving towards this stable region. Alpha is a helium nucleus, so it's got 2 protons and 2 neutrons, and it is charged 2+ because it doesn't have any electrons. You can also see it written like that as well. So let's have an example here. So radon 226 decays by alpha. And so the first thing is it decays into radon. Then of course you lose 2 protons, so that goes to 86. You lose 2 protons and neutrons and all, so that goes to 222. You can also plot this on the graph here, because we started with 88 protons and we started with 136 neutrons. So that is where our unstable nuclei started. And then of course it lost 2 protons and it also lost 2 neutrons, so it ends up here. So you can see that alpha decay is moving it towards the stable region. And finally there's a general equation which you need to recognize for alpha. That's the parent nucleus. The daughter nucleus loses 4 protons and neutrons in all, and it loses 2 protons, and that is your general equation. So that is alpha decay. So let's move on to beta minus decay. Now beta minus decay is caused by nuclei which are neutron rich, so they are over on this side here, and what they do is they want to lose neutrons and gain protons in order to move this way into the more stable region. And so how they do this, it's caused by the weak force. So what happens is the weak force is responsible for a neutron changing into a proton plus an electron, and that is what is fired out at near the speed of light, and that is your beta radiation, plus an anti-lepton neutrino. Now you have that to balance up what's called the lepton number, which is no longer in A level. So you just got to accept that if you produce an electron on this side, you have an anti-lepton neutrino on this side to balance up that number. Now we can look at this with quarks as well, because a neutron is an up, down, down, and that changes to an up, up, down, plus your electron, plus your anti-electron neutrino. So that is how you'd show it with the quarks as well. Now, it's helium-6 is an example that decays by beta minus radiation. So of course what we do is we lose a neutron and that converts into a proton, so you've got a 3 there, and you've still got 6 at the top because you've still got the same number of nucleons in all, which are protons and neutrons. And of course that means that you force this number to be -1, so that's where that symbol comes for the electron or for the beta particle, and you've got your anti-lepton neutrino there. And we can also show it on this graph here, because we started with 4 neutrons, we started with 2 protons, we went to 3 protons, and we went to 3 neutrons. The neutrons went down by 1, the protons went up by 1, and you can see it moves that way, which you can see in that diagram there. So that is beta minus decay. Finally, you also need to recognize this general one as well, where the parent nucleus decays into the daughter nucleus, which has 1 more proton, and your beta particle and your anti-lepton neutrino. So if we now move on to beta plus decay, which is a positron, which is an antiparticle of an electron. We can write it like that, or we can write it as a beta plus particle. Now it's caused because elements which are proton rich can decay by beta plus, and they tend to be lighter elements down here. And you can see that to become more stable, they need to lose protons and gain neutrons to move into this area here. So inside the nucleus, what happens is a proton changes into a neutron and a positron and a lepton neutrino. Now the lepton neutrino is there to balance the number here, because these are leptons, and for the number to be 0 altogether, because you've got no leptons on this side, you just need a neutrino. Again, that is past A level now. We don't have it in A level syllabus. So that is what is happening inside the nucleus, and that's caused by the weak nuclear force. Again, we can write that in terms of quarks. So we've got an up, up, down makes a proton, and an up quark changed into a down quark, which changes it into a neutron. It emits a positron and a lepton neutrino. We can also show this using an example. So fluorine 17 decays by beta plus decay. So of course we've got a proton changed to a neutron, which means this will drop by 1. That number stays the same, and that gives us oxygen. So finish off the equation, we have that as our equation. And of course again, the general equation would be the parent nucleus. We've got 1 less proton now because it decays into a neutron, and so we get that. And that is the general equation for beta plus decay. Putting it onto a neutron proton diagram, we started with 9 protons and we started with 8 neutrons. So that is where our nucleus started. And of course we lose a proton, and that converts into a neutron. So we finish up here, and you can see that that is moving towards the stable region there. So finally, what about gamma radiation? Well, gamma radiation doesn't change the element. So it normally follows an alpha or beta emission where the nucleus is still left excited and has too much energy. And so the nucleus loses energy by emitting a photon in the gamma range of frequencies, and that is your gamma radiation. And there's no change in the element, which means the symbol for gamma has to be 0, 0, because if you put it into a nuclear equation, it causes no change in the element whatsoever.